Hi again. If you've been watching some of these other videos I've been making about Hopper, about the language, about Hopper on 6502, this video is slightly different. It's going to be under a playlist called Hopper Internals, and this is probably the overview video to sort of lead that with. So it'll be a little bit of a longer video, a little bit of sort of stream of consciousness discussing the motivations of why I got to where I got to, and what the history is leading up to this. I will then do smaller videos for specific topics, and that'll probably be driven by any interest I get in the subject or topics I feel I need to cover. I've written a document about over a year ago which described my motivations. I'll add a link to the document in the video. It's actually on the GitHub site as well. I'll use, by way of example, I wrote this basic interpreter, Tigger Basic, of course, as a non-trivial sample app for running on the 6502. So this version of Basic runs on the 6502, and it's just less than 4,000 lines of Hopper code to make a basic interpreter, and illustrates a lot of the features. Hopper on Windows is a substantial platform too. The Hopper compiler is written in Hopper. The shell that I use here is written in Hopper. The editor is written in Hopper. The entire toolchain, debugger, everything's written in Hopper. So Basic's not the only big sample program, but it is one that's easy to discuss. So let me go back to the document and let's see what is where I should start. So I've worked in the software industry since the 80s, and I started in the first commercial products I did were in Turbo Pascal, which had a big effect on me. But most of my time was spent working in C++, and then more recently in C#. I'm retired now, so I can go back to my roots and do things I enjoy. So things like Turbo Pascal played an influential role in this, so that's why I've seen other people attempt to do things like port something similar to the Java VM to these small machines before, and it's a bit of a disaster because it was never intended to run on these little machines. So I decided not to do objects from the beginning, and I don't feel like they're a necessity anyway. I think units in Turbo Pascal were a really good idea. So you get the encapsulation of that you would from an object-oriented environment, but without having the objects and all the baggage that comes with them. Many of these choices and decisions are going to be subjective, and you may not like them, but it is my language, so I'll do it my way. There's a whole file and path system involved here, and especially it runs on Windows. I've had it running on SD cards on microcontrollers before. I made some choices in the paths. I don't allow special characters in file names or folders, so only letters and digits. I use / as the path separator. I don't allow spaces in paths, so that you don't have the ambiguity when you have command line options as to whether, when you're trying to pass a path to a command line option, you've got to put in quotes and all that mess that happened with Windows. We can talk later about whether I think paths should not be case sensitive, although that's a tricky one to do. Like if you consider that this needs to run on a Raspberry Pi at some point on Linux, but we'll get to that. Strictly speaking, there's no pointers in Hopper. It's a managed platform, so objects are managed by the garbage collector. So there's no malloc or new or free. So there's no garbage. There's no memory leaks. The closest we get, and it's also single-threaded, and the combination of those two things means that it's a stack machine. So you've got a stack machine that's single-threaded, which means that the stack is actually just a really simple version of a live list of objects for your garbage collector. So the two things are pretty closely related. There is one form of object that it is possible to, say, have null pointers in. and that would be delegates, because they're function pointers. So you can define a delegate type, a named type that's a delegate. There's only 3 named types in Hopper. Enumeration types, like this enum down here. Something called flags, which is a variation on enumeration types. And delegates can be named. All other types are anonymous, like this dictionary and that dictionary. And duck typing is used to compare whether 2 types are the same. So these delegates, let's go see where they're used in this file. They get assigned to point to the different virtual machine methods for the basic interpreter. So yeah, strictly speaking, you could have an uninitialized one, because all variables in Hopper are initialized to 0 by default, and that includes delegates. So you could conceivably call a delegate which has not been initialized. So here, in this code here, we're getting the current method from using a bytecode from an array of a dictionary of delegates. We're assigning it to this delegate, and then over here we're calling it. So if we didn't initialize it here, we might have a bug. But at least this can be easily caught by the runtime. But it'll be a runtime failure, not a compile time failure. So that's the one exception, the one place where it's possible to have an uninitialized pointer, even though there's no pointers in Hopper. Back to this, so no threads. I just do no threads just because it's simpler just to have a single thread. So much easier to get the thing bug-free. And I mean bug-free. This is amazingly stable. I cover a lot of this sort of convention in other videos, so I won't labor the point on these. Let's go back to this again. In terms of types, if you're familiar with the curly brace and semicolon languages, then you've seen a lot of this before. The value types in Hopper are 16 bits wide, with no exceptions, including things like a Boolean is 16 bits wide, and a char is 16 bits wide. I currently only use the bottom 8 bits, which means in future I could do a better job of supporting Unicode, for example. Right now I just do ASCII without changing the binaries. I experimented early on with different widths of stack slots. So like a byte stack slot to try and make it more efficient. And on the ESP32, I also experimented with 32-bit stack slots, and on Windows with 32-bit stack slots. My conclusion after about 2 years of this is that 16 bits is the place to be. And you're limited by 64K at that point, because things that go onto the address, onto the stack, and the call stack's the same, might include things like addresses in your program. Or obviously data, like locations of data. So you're limited to 64 bits by 16-bit slots. On Windows, in the runtime, you can launch one executable from another. You can chain things together. And each of those has a 64-bit code space. So you're limited inside a single program by 64 bits, but not the platform. Strictly speaking, if you look at how the file format is organized, if we examine how the file format looks, the real thing that's limited to 64 bits is the amount of code per method or per function. It would be possible to easily modify the system so that you could get beyond the 64 K limit for the program, but just have it so that the methods and functions are limited to 64K. And it's actually less than 64K. It's half of that. It's 32K, and it's because the code inside each functional method is completely relocatable, because all the jumps are relative jumps. So they jump forwards or backwards by an offset, and that offset is stored in 16 bits, hence the 32K limit. So your ultimately our methods and functions are limited to 32K by the fact that they need to be able to jump from one end to the other with that 16-bit offset. So yes, let's see if I have anything more to say about the value types. I think I'll talk more about what flags are later as to why they're different to enumerations. They're very similar to enumerations. It's very strict type-wise. You can't just do what you can in C, where you just assume that you can treat an integer like a Boolean, etc., or even just casting types. There's two different versions of the Hopper build. There's a checked build. It's like the old Windows checked build. So if you're running the checked build, it's much stricter in terms of checking ranges and checking for overflow and stuff. So if you try and cast a int to a byte, it'll make sure that that int value was only 0 to 255. And then once your program is debugged and running smoothly, you can just make you can make it not be a checked build, which it doesn't do. It'll just run wild and assume that those kinds of casts are going to be safe, or that you're not going to have any division by zeros, or you're not going to go beyond the end of a collection like a string or a list. Seek and go to an index that's outside of the range of valid values. So with a check build, it'll check all that, and then you can strip that all out once you've got a production product that's running smoothly. Reference types. There's two things that happen with reference types when they get pushed onto the stack. Like if you push something onto the stack to do something with it, you're not really making a copy of it. So it does reference counting. There's limitations there. There's only 1 byte given to the reference count, so it's highly unlikely it'll ever be met. I've never seen it get anywhere near that. But it'll blow up in the checked build if you do try and increment the reference count beyond 255. So if you push a copy of something on the stack, it's not really a copy, it's an increased reference count on something. Like when you pass a reference type into a method as an argument, it'll just increase the reference count, and when it comes back, decreases the reference count. And when the reference count decreases to 0, the garbage collector cleans it up. Only objects that are on the stack are reference counted. So, for example, if you create a list of strings, the strings within the list are not reference counted because they belong to the list. So when the list is cleared up, when the list hits 0 on the reference count, it cleans itself and all its items in the list, and that works recursively as well. So that really simplified garbage collection because your live list for your garbage collector is the stack, and once you pop something and something goes out of scope and it goes down to 0 counts in its reference count, it just gets garbage collected right then. So it's not a garbage collector running on a different thread or anything. It happens real time as it's needed, and it's not very expensive either. The expense there is underneath the hood is like a sort of a C-like version of malloc and free, and when you free something up, it has to collect that block into the free list and merge it with neighboring free blocks. So that's the only cost of the garbage collection. And you obviously have a similar cost on creation, where you're looking for, in like a malloc kind of algorithm, and you're choosing to have a first fit or a best fit, and the current algorithm I use is a best fit algorithm because I'm more concerned about space efficiency than time efficiency right now, and that seems to be okay. It doesn't seem to be slowing me down much. How do I get away with allowing the content not to be garbage collected, the content of a collection? Well, I made a decision early on to do deep copies on assignment. And if you copy on assignment, then you don't end up with the same item inside a collection existing in more than one collection ever. So it's expensive to copy on assignment, and you have to be aware of it when you're writing code. So you might it might encourage you to not make a copy or pass a reference into something, like a ref argument. Or so you have to be aware of that. If you have a big array of bytes and you keep passing it around and making copies of it, it's expensive to copy on assignment. But on the plus side, it has made garbage collection really easy and really fast. So yeah, it's single-threaded, which makes it very easy too. And references are copied on assignment, always copied on assignment, which makes it easy. Alrighty, what's a flag? I got the idea of flags from the flag attribute in C#. So in C#, you can add an attribute to a enumeration type called flags. And if you do that, then you can do arithmetic on the enumeration values. So you can do bitwise arithmetic on your enumeration values. So an example of that, let's go have a look. Do we have the keyboard here somewhere? I guess I have to go to a different program to see this. No, it must be in here. Oh, it's in I/O. There we go, keyboard. So in keyboard we have flags for our key types, and you can see that they're bit coded. So like Shift and Control and Alt are bit flagged, and there's a mask to get rid of those. Shift, Control, and Alt. And this my keyboard mapping is quite clever. I've got another project on Hackster that discusses this. It's a very one-to-one relationship between these and PS2 key codes. But I've extended it a bit as well to, like, it has mouse clicks in it too. So you can use your keyboard API to also do your mouse clicks, including scrolling. It's quite neat. It's worth examining at some point. I'll probably do a video on it, on keyboard alone. But anyway, so this is a good example of where it looks like an enumeration type, but you actually add in all these things together with bitwise operations. So it allows that to work. So you can mask them out with ands and ors like that. And you can do that kind of operation. This and something or other. And if you do this, what you can do is you can stop hacking to happening with enums. So if you looked at how enums are done, enums don't allow any arithmetic operations. They still allow you to set the numeric value at some point, like start this from 32 onwards. And of course, the first one's 0, and then they increment as they get values. And then you can reset it at some point to some value. But you can never do arithmetic on these. So you can't be sneaky and hack away. If you want to do that, then you need to make them into not enums, but flags. So instead of using an attribute like C#, I just made a different type, flags. My switch is slightly different. I can handle strings in my switch. I've spoken about units. Oh yes, how does Hopper work? It's a 2-pass compiler. In the first pass, it collects all the definitions. So C needed header files for this, which is like terribly inefficient when it comes to scale. Like very large files, it's very inefficient to have. And then you start using hacks like precompiled headers. Pascal used something called a forward declaration, so that you could, otherwise you can't do sort of circular, like function calls to things that don't exist yet. Whereas more modern languages like Java and C# tend to do more than one pass. They needed to do a single pass with small machines when they didn't have the resources to keep the whole thing in memory at the one time, but we do now. And that's why my compiler is only running on the big machine on Windows. I'll never run my compiler on the little machines. It's because it's a 2-pass compiler. So the first pass connects all the definitions of the global level items, and then the second pass compiles the content of all the methods. In other words, the bits between the curly braces. On the second pass, it compiles the bits between the curly braces. So the first pass collects all the bits and pieces, all the high level stuff. Second pass compiles the bits between the curly braces. I have preprocessor directives at some level. I have the concept of public and private as well, mentioned encapsulation with units. So the way I do public and private is a lowercase character at the start of an identifier is a private method or private member. Uppercase character at the start of an identifier is public. And I only allow letters and numbers in identifiers, and I don't allow underscores just because I think they're ugly. I mentioned delegates being the only pointer type. I think that's about... I mentioned this. I've got a video in the language section about what this is, considering I don't have any objects. It's a sneaky way of getting some quite clean syntax sugar into the language. I mentioned child programs you can launch, and that's how the shell works. The shell launches child programs. So yes, constraints. It's designed to run on small platforms, including legacy 8-bit processors. So the bytecode is a byte. It's limited by that. So each instruction is a byte. Means there'll never be more than 256 instructions, but I haven't even used 80 of them yet. Oh, not even close. Each instruction can be 1, 2, or 3 bytes long. So 1 byte if it has no operands, and then it can have a single byte operand, which is typically an offset, like that. Or it can have a 2-byte offset as well, optionally. So there's quite a few instructions where there's 2 versions. There's the byte version and there's the word version, so that I can keep the code as small as possible. I mentioned that the method size is limited to the distance of an offset jump. And that's no limit. Yeah, there's limits, like the limit on the number of items in a list is also limited by 16 bits. Arrays are an interesting choice. Limit on dictionaries. I've only got 2 types of keys that are supported in dictionaries. I can support a string as a key, and I can support a uint as a key, of which bytes and chars are a subset of units. So uints. So these are integral types that are positive. So you can't use a long, you can't use an int. And those are the only 2 types of keys used for dictionaries. So I've only got 2 hashing algorithms. The one makes a 32-bit hash out of a string, and the other one is a very simple hashing algorithm. It uses just as a mod of it's the mod of the current capacity. So take the key and mod it by the current capacity, and you get the hash for the integral keys. Yeah, so a list is limited to 64K of elements in a list. Arrays were designed from the beginning to be something that would be super efficient on little machines. So you can only declare the size of an array at compile time, not at runtime. It can't be it can't grow or anything. Arrays can only contain value types, so the ones listed there. And I'll mention why float and long are not value types. I'll mention that in a second. It's a super efficient structure, and in fact on the 6502 a boolean is a single bit, so you can make a boolean array, and I was sort of inspired by the way Turbo Pascal used to have sets, and they had a 256 member limit in sets where each member in the set took up 1 bit, so an efficient type. So I'm not limited to 256, but I do use 1 bit per entry if it's a set of booleans, an array of booleans. Anyway, a very efficient type on small devices, very fast access compared to walking through a list. I do have some other content out there. Okay, let's talk about floats and longs if I haven't already. So floats and longs are 32 bits. I don't do doubles. I think float is fine for my purposes. Maybe I'll do doubles at some point in the future. But because they're 32 bits, they are treated as reference types. They're surprisingly fast, but I wouldn't go about doing any heavy lifting with those, that involves tight loops and lots of operations with those 2 types, simply because they're reference types. Rather use a uint or some scheme to use more than 1 uint to do that. but they work pretty well on the 6502. I don't have float implemented yet on the 6502. I only have long implemented on the 6502. Okay, how am I doing? 25 minutes. I think that I should probably stop there. I've done another related video on, if you look in the language playlist, on ifdef, and that talks about, and I've got another one that's worth watching, and then after that there's another one in the 6502 channel which is about TinyHopper, which talks again about reference types versus value types. Anyway, thanks for sitting through my reading of my document, and I will put other videos into this channel that are topic specific on these topics that are a lot shorter than this.